second part of the meetup. I'm Carol. I'm another engineer here at Buoyant, and I'm going to be introducing my coworker, Kevin, who is an engineer here as well. And Kevin is going to share how and why companies are moving their architectures from REST-based APIs to gRPC. And please enjoy. And here's Kevin.
Yay. Okay. Yeah, that's right. So I'm about to give a talk about the history of web APIs. It's like the most exciting thing you've probably ever heard. And I did like a lot of research recently on kind of how APIs evolve, and it got me thinking about AJAX. Has anyone used AJAX before or is familiar with the term? AJAX stands for Asynchronous JavaScript and XML. And there is basically no XML involved in AJAX anymore. Nobody uses XML in the browser at this point. So anyway, I'm going to kind of talk about how companies evolve their APIs. Because as you just saw in Leo's talk, like the move from monolith to microservices, communication between services becomes really critical to the overall infrastructure. And we can do a lot in terms of managing that communication, and of course things change over time. So gRPC is maybe some of the new hotness around how services can talk to one another. So I'll talk about how we got there, and then I'll talk about how Linkerd, which is really like a traffic router at heart, can really help with overall communication in your sort of API setup. Okay, and I don't give a lot of talks. But I'll tell you a little bit about myself, and then you can always stop me if you have questions, or we'll take questions at the end, that kind of thing. Okay, so this is me, software engineer at Buoyant. So I've been at Buoyant about 4 years, and when I first joined, I was working on Linkerd 1, which is written in Scala. And more recently, we have launched Linkerd 2, which is a combination of Go and Rust. I work predominantly on the Linkerd 2 control plane, which is written in Go. Before Buoyant, I was at Twitter for 5 years, and I was there for the monolith, the microservices decomposition, very similar to what OfferUp went through. So I kind of have some perspective on that. And I guess also I have like a decade's worth of experience using legacy APIs, so now I can give you some more context. I'm also a member of the LGBT community, and I really like to talk about how tech can be more inclusive for people from all backgrounds. So you can come find me afterwards to talk more about that. And so now we'll just get right into it. Okay, so I want to talk about gRPC. gRPC is a CNCF project, just like Linkerd is a CNCF project. So CNCF is the Cloud Native Compute Foundation. It is an incubator for open source projects, and it's focused on these cloud native technologies. And so you can think of Linkerd, Kubernetes, gRPC, Prometheus. These are all CNCF projects. They all work really well together because they're all designed for running large-scale distributed systems on the cloud. So, and gRPC, I think, really epitomizes that for me. And so I want to talk about how we got to gRPC, and also how gRPC and Linkerd can work together to give you kind of robust APIs between your services. Okay, so we're going to go way back here. So in terms of evaluating an API, there's really two things that I think about when I'm thinking about an API. One is the serialization format, and the other is the transport protocol. So serialization format is really just how you take the data in your application and turn it into bytes, like a string of bytes. And then when you receive a string of bytes from an API, how you take that and turn that back into data, right? So that's the serialization. The transport protocol is how you get the bytes across the wire. So from like the server to the client, once you have this string of bytes, like how does it actually transmit across the wire? And there's lots of different ways of doing this, unsurprisingly. But so when we are going through and talking about APIs, we'll really be focusing on this. Okay, so in the beginning there was REST. And REST is a very loose term because REST is kind of a concept and not necessarily a technology. But I will talk about REST now in sort of its properties. So REST is really all about objects or sometimes resources, right? And the idea is that if you have a web server, you have a bunch of objects. Possibly those objects came from like a database because you're running in like a database model, and you really just want to expose them to your clients. And so REST is one way to do that. The thing about REST that was really interesting is that it leveraged the HTTP 1.1 protocol. So prior to REST, there were sort of different types of APIs, and they really mix the serialization format and the transport protocol, or they use like a lot of bespoke transport protocols. But with REST, it really attached itself heavily to the HTTP 1.1 spec. So the APIs themselves were just derived from HTTP itself. So the endpoints are really just URL paths, and then you could use different types of HTTP methods to access them. So like the example I have here is, let's say that you had a books resource because you're running a library app or something like that. You can serve different endpoints that will return lists of books, right? So a GET request to the books endpoint returns all of your books, whereas like a POST request can create a new book and add to the collection. And the idea is that you have this standard set of APIs for all the objects in your system. And then the other thing that REST did well is that it divorced the mechanics of the API, like the transport, from the serialization format itself. And so lots of REST APIs would support multiple formats. So if you have a client that expects JSON, you can send it JSON, or you can use XML. A lot of like purely REST-driven web applications also put HTML in the mix, right? Like a URL is a URL, and if a client goes to a URL and wants HTML, they can just get HTML back. But if it's a program that really needs XML, it can request that format instead. So it's kind of all part of the REST philosophy, I guess. Okay, so let me just make sure I'm not talking crazy. Yeah, and then the other thing to note is, like, since it's using HTTP 1.1 protocol, it is tied to HTTP 1.1 and some of the limitations that it has. So one of the limitations with HTTP 1 is that it's a single request and response per connection. So if I create a connection to a web server and send it a request, as a client, I just have to wait until the response from the web server comes back before sending another request. If I want to send two requests to the web server in parallel, I have to create two connections, right? And so that kind of constrains the amount of data that I can send and receive based on the number of TCP connections that I can build, which is what Leo was alluding to in his talk too. Let's see. Okay, so then over time, so REST had all these different formats, right? XML was kind of the canonical one, but JSON was also there. But XML is like a very verbose schema. Like if you've ever seen an XML document, I guess I could put a snapshot in. It'll have like tons and tons of like HTML-like tags in it, and they'll have types, and then you can import other types from other XML specs, and then you can send around the schema file so that your users can validate that the schema of the XML document that they received is valid. Anyway, it becomes very cumbersome, basically, to structure the data in that way, and people kind of just, I would say, gave up on it a little bit because JSON was there, and JSON is like sort of the opposite end of the spectrum. It's really just key value. JSON schema lists, like you have a key, and you can assign it some values, and then that it's like a very concise representation of what you're trying to express. It also means actually that the bandwidth that a JSON API takes up is a lot less than XML, and we saw this at Twitter. So when we finally turned off the XML API at Twitter, the API bandwidth dropped because everyone switched to JSON, and JSON's just less data overall as a serialization format. But with no schema, things get really crazy really quickly, right? And like it's too hard for us mere mortals to resist the temptation of just like throwing arbitrary data into an API payload because it's just key value and you can sort of add and remove. And so I would say kind of over time we lost the object model from REST. Like we're no longer talking about objects, we're just talking about a big blob of data that has some keys and you expect some values back. And then you sort of get into this world where the server may be sending down these JSON blobs, but there's no way to validate that it's actually the right data or it's the version of the data that you expect. And then the clients can run into lots of issues, right? If they're not receiving the data in the format that they expect, and there's no way to actually validate that. Think like basically null pointer exceptions. Like if you expected a field to be present in the JSON payload, you have no guarantees that it's actually going to be there, and your code needs to sort of work around that. So in this era, I would say things got pretty messy, right? And this is sort of where we are today for a lot of applications, is like just sending back these giant key value blobs. Okay, but there were some very large tech companies that were concerned about this type of problem, and so they took a different approach to APIs with structured data, and they kind of evolved at roughly the same time. By the way, not all of my summary here is historically accurate. This is sort of my observation of it. So who knows which one came first, Thrift or Protobuf, but these are two different technologies for managing structured data and APIs, and Facebook was working on one and Google was working on one, and they both sort of hit the scene at the same time, but they were remarkably similar, and they solve a very similar problem. And so the way that they solve the problem is by creating these API spec files. So you sort of define all of your API objects in the spec file, and you define your endpoints. So like the parts of your API that be called, which objects they accept and which objects they return. And that spec file is language agnostic. So it's written in this sort of DSL setup, and it kind of describes how your API works. And then both projects also include a generator that will build language-specific libraries that interface with the spec that you put in the spec file. And the big advantage there is then you can really leverage language-specific features in the, and we call them bindings, in the bindings for the API. And so if I'm a client and I use the Ruby bindings for the API and I send my data, and then the server receives it and it's a Scala server, like the API objects look like native Scala objects when it receives them, but like when I sent them, they were native Ruby objects. So it's a way for multiple languages to work together. And yeah, so in terms of a serialization format, the serialization format is binary, right? So at the end of the day, we have these API objects. The libraries produce this string of bytes that's binary data, but it's specific to the technology that we're using. So if it's Thrift, it's like a Thrift binary payload, and if it's gRPC, or sorry, if it's a protocol buffers, it's a protobuf binary payload. And those things aren't really interoperable, although they are now, but sort of at the time that these were both taking off, you couldn't really send Thrift data to a to a protobuf service, and you couldn't send protobuf data to a Thrift service because they weren't really the same. The other interesting thing about these two technologies is that Thrift also came with its own transport protocol. So REST was over HTTP 1.1. Thrift wrote their own transport protocols. And actually, it wasn't just one protocol, it's multiple protocols. So the basic Thrift protocol is a framed protocol. So it will take a Thrift message, and it will first send the size of the message on the network stream. So it'll say, like, this message is going to be 40 bytes, and then it will send the message, and then the client or server can receive it. But that didn't include compression or multiplexing, and so a lot of these things got layered on top of Thrift. So the short story here is that the Thrift transport protocols there were many of them, and they got pretty complicated pretty quickly, and they're a little unrelatable because it's Thrift, and nobody has ever really done a lot of research into like the Thrift transport protocol. The other interesting thing is that protocol buffers got open sourced without any type of transport. So at Google, I'm sure they were sending byte streams around that represent these protocol buffer messages, but they didn't actually open source the technology for how they were sending protobuf back and forth. So it was really, as far as I could tell, protocol buffers was used to write data to disk and to read it back out, but there was really no networked communication involved with the original protobuf project. Anyway, but this was like sort of a very like large-scale computing approach to solving the structured data problems. And there were sort of two technologies, they're kind of rivals. But meanwhile, HTTP2 is being developed. So HTTP2 was a major revision of the HTTP spec. It I think it was formalized in 2015, but the previous revision to HTTP had come out in 1997, so it was almost 18 years. And HTTP2 is really like a major upgrade for how HTTP communication works. And it solves a lot of the problems that we saw with HTTP1 in the first place, especially this multiplexing problem, the idea that a single request and response could be sent on a connection. All of a sudden, you can set up one TCP connection, and you can send a bunch of requests along a connection and receive a bunch of responses all at the same time. And there's ordering for like the way that the requests are processed, and that's really good. There's also built-in compression with HTTP2, so the payloads that are sent over the wire are smaller. And there's sort of more advanced RPCs too. So like in a standard H1 setup, it's really just a request and a response. And in H2, you can send back a stream of data. You can, the server can actually just sort of arbitrarily push data down to the client without the client explicitly asking for it. So it's just a more sophisticated protocol for sending data back and forth. And the other thing that's really awesome about H2, which we're now seeing in practice, is that it uses many fewer TCP connections, and it makes it much easier to add TLS everywhere, because TCP connections with TLS are expensive to build. So like it takes a long time to set up a TLS TCP connection initially. So if you're not setting up as many connections, you can actually add TLS everywhere and not take the latency hit like you would in H1. So this is pretty great. And that actually brings us now finally to gRPC. So gRPC is sort of a marriage of protocol buffers and HTTP2. So for serialization, it uses protocol buffers, which is structured data. It has really strong language support. There you can create protocol buffer bindings in every language under the sun at this point. But Java, Python, Go, Ruby, so it's well supported. And then all of the data that's serialized from protocol buffers is sent over an HTTP2 connection, and the HTTP2 spec is really great, and it also it fits into the existing HTTP infrastructure. So if you had an HTTP proxy, that proxy can continue to proxy HTTP2 traffic. Browsers, are even updated to speak HTTP2. Web frameworks like in Go will just automatically upgrade to HTTP2. And it's a spec that people understand at this point, unlike, I would say, Thrift, which was kind of like a black box all along. So kind of like, I think that to bring it full circle, like REST was really like an invention in and of itself 15 years ago. And I think what REST did really well was it divorced the serialization format from the transport protocol, and it used a known good transport protocol, which was HTTP1, and that's what was available at the time. And then the serialization format was really flexible. With protobuf, we have this structured data now, and that has very strong language support. And then we also have a very robust transport protocol underneath it that can enable a lot of really cool features. So you can add streaming to your APIs. The clients can stream data to servers can stream data back to clients, because you get a lot more sophistication there. Does that all make sense? Cool. So now I want to talk about Linkerd. So we moved on to Linkerd. And the reason why it makes sense to talk about Linkerd at this point is because Linkerd lives and breathes transport protocols. That's what it cares about the most. And so Linkerd loves your APIs. Basically, Linkerd has multiple components, which I'll discuss right now. And this is Linkerd 2, which is different than what OfferUp was employing. But at its heart, Linkerd is building connections and sending data across those connections, and so it needs to understand these protocols really, really well. And so it turns out it actually does understand gRPC really well, and it can give you a lot of information about how your gRPC apps are performing. So quick Linkerd 2 summary. We'll start with the data plane. Kind of the functionality is divided up between data plane and control plane. So on the data plane side, this is where your application is running, and you would run with a Linkerd proxy sidecar alongside your application. And this is Linkerd 2 is Kubernetes specific, so we use the pod model. So in the pod model, you have a container that has all of your application code, and that runs in a pod, and then we add a Linkerd proxy container to that pod. And all traffic in and out of the pod gets routed through the Linkerd container automatically. And the proxy is written in Rust. It's very lightweight, very small and fast. And then the proxy, and so we would be running hundreds or thousands of proxies in like a standard Kubernetes deployment. And then we have one centralized control plane in the Kubernetes cluster that controls all the proxies. So the control plane's kind of architecture is described up here, but the main things to think about with the control plane is that it pushes configuration out to the proxies. So it gives the proxies all of their routing information and all of their service policies, that kind of thing. And then it pulls metrics data from the proxies. And we use Prometheus to do this. Prometheus will scrape metrics from the proxies, and then we can give you lots of stats about how the proxies are routing all of your traffic. And that gives you a lot more visibility into your application as a whole. Okay, let's see. So, yeah, and so this works really well in conjunction with gRPC. So I'm going to cover just a couple things that that you can gain by using Linkerd and gRPC together, and then I will go through a quick demo. So the first thing is request level load balancing. So let's see. Linkerd is already load balancing your traffic to all your backends, and this is what Leo was talking about in his presentation. But in a standard Kubernetes setup or in most environments, load balancing happens at the connection level, right? So when a new TCP connection is established from like a client to a server, that connection will be load balanced. So like if there's 10 servers to choose from, it will pick one of them. And then the next connection that gets created will go to the next server and that kind of thing. Well, since gRPC is so fancy and it uses multiplexing over HTTP2 connections, you actually don't need very many connections, or really you just need one connection. And so connection level load balancing kind of breaks in this model, right? Because like if you are sending your traffic and you're expecting it to go to 10 different backend instances, and we build a connection to one of the backend instances, all of a sudden we have all of the infrastructure that we need to send all of our traffic, and so all of our traffic goes to one of the backend instances and doesn't get load balanced at all. And so really you have to get away from connection level load balancing in a setup where you're using HTTP2 as transport. And so for that, we really need request level load balancing. And what request level load balancing means is that like rather than treating everything as just a TCP stream, we need to look at the data that's on the stream or on the connection and figure out what's a request and what's a response. And when we see different requests, we can actually send them out to different servers. So in I guess the charts here is like basically in a gRPC world, like you might server A may send all this data to the first instance of server B, but if you put Linkerd in the mix, it will actually accurately farm them all out to all of your backends. And I'll show you a demo of this, which makes, I think, a lot more sense. But and then with Linkerd in the mix, you also get AdaptationAware Observability. So since it is doing protocol detection, it can actually tell you a lot more about the types of traffic that are flowing on these connections, rather than just sort of raw TCP bytes. Because like if you're just talking about like a TCP load balancer or TCP router, all you're really going to get is like the number of bytes sent on the connection and the number of bytes received. And furthermore, if we're just talking about an HTTP router, if we're like just speaking in terms of strict HTTP, you'll probably see requests and responses. Number of requests served, number of responses received, successful requests, that kind of thing, and you can calculate a success rate, and that will tell you the overall health of your service. But in a gRPC world, you may have multiple different endpoints served by a single service, and we can actually, since we're inspecting the traffic, tell you how every endpoint is performing. So we can sort of further divide up all of the stats in order to see really granular data about all of the endpoints. So like this is an example from the Linkerd stat output, which I'll show off. But you can actually see how individual method calls are performing, and so it's a lot more specific data about what you need. Okay, and then the last thing that I think Linkerd really helps with is client configuration. So let's see. So gRPC is like an API standard, and it suffers from the same problem that I think all APIs suffer from, which is this thing that I call the service owner's dilemma. So basically, if I have a service and I provide an API, and lots of people throughout my organization are relying on my API, they could configure their API clients in all sorts of weird and wacky ways, and that could actually cause a lot of problems for my service. So all of a sudden, I could be woken up in the middle of the night because somebody who calls my API has misconfigured their client. So a really good example of this is a service or a client that sets like a really aggressive timeout and just says, well, I expect every request to your server or service to respond within 50 milliseconds. And if it doesn't respond within 50 milliseconds, I'm going to automatically retry 3 times, hoping to like get the right request. Well, all of a sudden they've increased their traffic to your service by, 4x. And so basically, like when I was at Twitter, I worked on the tweet service, which turns out lots of apps within the Twitter infrastructure really needed access to tweets. And so we had dozens and dozens of clients that were always calling the tweet service, and we would often be woken up in the middle of the night because a client had been misconfigured and was like doing something really bad that impacted our services metrics. So recently, Linkerd introduced this idea of service profiles. So now if you have a service in Kubernetes, you can create a profile for it, and that will tell Linkerd sort of a lot of the characteristics of your service. It will tell Linkerd what the expected timeout is for all of the endpoints, if any of the endpoints are retriable, and then Linkerd can retry automatically. That kind of thing, and we're sort of adding more as we go. And this really takes the control over client configuration and puts it back into the hands of the service owner. Because really, it's like the service owner who knows how long it should take for requests to complete. You don't really need all 50 of your clients kind of guessing how long it would take for requests to your service to complete. This snippet of code is actually from Finagle, but like literally within the Twitter infrastructure, this is how people would configure their clients for every downstream that they're going to call. And there's so many parameters here that you can tune. You have to set like a request timeout and a load balancer policy and everything else. And like basically, if you use a service mesh can take care of a lot of this for you, and your clients can sort of be a lot simpler. And then the more complicated RPC mechanisms can be deferred to the service mesh. And that's what Linkerd does. And I think it's really powerful with gRPC too. Okay. Any questions about that? I'm going to do yep.
So from a data plane proxy point of view, is there any extra logic that goes into the proxy data plane to support gRPC versus HTTP1? Because all it is request level routing or load balancing. So is there any logic that has to be added for gRPC?
Yeah, that's right. So not gRPC specifically. Since it uses the HTTP2 transport, it's just HTTP2 from the proxy's perspective. So the proxy will do protocol detection. It'll read the first couple bytes off of each connection, and then it'll figure out if it's HTTP1, HTTP2. We may eventually add support for other protocols. Otherwise, it'll fall back to TCP. But since gRPC uses a known API format, then we can actually use service profiles to give the proxy more information about the data that's being sent, and then it can apply policy at that level. But it's nothing outside of the standard HTTP2 spec.
Something maybe outside the context here. Is the Linkerd to start or to do anything like H1 to H2 upgrade?
That's right. Yeah. So if you have a client that is sending an H1 request, we will actually do upgrade to HTTP2 between the proxies. So like if you're right, it's basically the client sends its request to its local Linkerd proxy, which sends it to the remote Linkerd proxy, which sends it to the other application web server. And we can actually upgrade the connection between the proxies from H1 to H2. So it means we have fewer TCP connections and we can multiplex over those, even though the client itself may not
aware of it.
You may not be aware at all.
So you can do the same thing for ingress as well?
Yeah, not exactly. So Linkerd 2 doesn't offer much in the way of ingress. I'm not too. You mean Kubernetes ingress or?
Yeah, I think it uses a separate ingress controller, but then
Yeah.
it finally hits the last proxy that's before the ball.
Right. Yeah. So I think in that world, if it were H1 traffic on the outside hitting only Linkerd 2 proxy, as long as there was another proxy on the other end, that upgrade would happen. But I'm not positive. I would have to go look. Yeah. Okay. Oh, go ahead.
You talked about the centralized client config, so I was curious, does that centralized client config take precedence over what individual clients must be doing? For example, if somebody's too aggressive, but the centralized config says that you can't be so aggressive.
Yeah, so I think it would take a little bit of a cultural shift within the company, like within your organization, to get them to stop setting their client settings, right? I mean, the clients will always be able to configure their clients in whatever way, but once we have Linkerd in the mix with service profiles defined, you'd expect that client configs to be really simple, right? Like probably not set a request timeout at all and not have a retry policy. Kind of just assume that whenever they send a request, it's either going to succeed or it's going to fail. And in the background, Linkerd will apply kind of a more advanced.
So they can confidently remove any configs that they have.
Yeah. And that's kind of that sort of goes to the core of the service mesh philosophy in general, is like we should have really dumb web servers and web clients. Like there shouldn't be a lot of this like really complicated logic, like sophisticated load balancing algorithms, stuff like that built into your application. Like you should just assume that something else is doing that for you. Yeah. Cool. All right. So really quickly, I'm going to just give a gRPC demo with Kubernetes, and then we'll be out of here. All right. So I wrote this with all open source technologies, and these are the technologies. It's going to run on Kubernetes, which is how we deploy our containers and run them. gRPC for service-to-service communication. I also have a REST as well. Obviously, we're using Linkerd. Linkerd comes with Prometheus and Grafana, which are also open source projects. Prometheus collects metrics, Grafana displays them. They're really great projects. And then at Buoyant, we've written a few utility projects as well that anybody can use. One is called Building Blocks, and that will help you assemble like simple topologies in Kubernetes. And then Slow Cooker to generate a steady stream of traffic, and they're all up on GitHub. So when we deploy our application, it's going to look like this. There's going to be a traffic deployment that's sending traffic to a gateway deployment, and then the gateway deployment is fanning out traffic to two backends. One backend is a gRPC backend, and one is a REST backend. And I put this demo on my GitHub, so if you want to run it yourself, there's instructions in that repo. Okay, let's do this. All right, bump this way up. Okay, so in my cluster, I've already installed Linkerd, hopefully. There we go. And I can run Linkerd check to make sure that the control plane is up and running. So the control plane is already there, but I have my local application. And my application is defined in a file called app.yaml. And this is, should I bump that a little more? Let me bump up a little more. These are just Kubernetes objects as deployments and services that will route traffic between my containers to build the topology that I showed. So we have a REST backend, we have a gRPC backend, we have the gateway service itself, which fans out to the REST backend and the gRPC backend. It's configured to do that. And then we have a Slow Cooker deployment, which is sending all of the traffic to the gateway, and with kind of these settings. So pretty basic, but it leverages some fun open source technology. So let's just go ahead and create this app in our cluster. So if we run kubectl apply, kubectl get pods, so it's setting up a bunch of pods for our demo, and I can actually run Linkerd check proxy to check the data plane. And so it's sort of, this will tell us when the data plane proxies are ready. So I'll let it spin for a moment, but the proxies are written in Rust, so they should come up pretty quickly, hopefully. But basically, none of the pods will receive traffic until the data plane proxies are up. And at this point, I am using Linkerd to run both of the backends, but not the gateway or the traffic service. So if I run kubectl get pods, you can actually see that I have a single traffic pod. This is the one that's generating the traffic, and a single gateway pod, which is fanning out to 3 gRPC backends and 3 REST backends. And in terms of the number of containers, the gateway and traffic pods only have 1 container because they don't include the Linkerd proxy yet. But I added the Linkerd proxy via an annotation in the config to the backends, which means that we can already get some stats about how the backends are performing. So if I run Linkerd stat deploy, this should show me my deployments. And so, yeah, you can see we have 4 deployments. 2 of the deployments are reporting stats because they have Linkerd injected in them, and 2 are not. So you can already get kind of some basic stats about what's happening with these deployments. And actually, it hasn't been a full minute yet. So they should be receiving about 60 requests per second based on the traffic that I'm sending them. And you can see they're at 100% success rate, so they're successfully serving all their requests. And then we also get percentile latency stats that shows us how long it's taking to serve requests. So, and then also the number of TCP connections. So like an interesting thing here is we have a REST backend and a gRPC backend. There are 24 TCP connections to the REST backend because REST needs to use multiple connections to get its requests. And there are only 2 TCP connections to the gRPC backend, which is interesting because we have 3 gRPC backends, and that means it's absolutely impossible that they're all receiving traffic. So let's actually look at that. So if I run Linkerd stat pods, it's going to wrap. There we go. Yeah, so this is sort of what I was saying is we're sending both of the deployments 60 requests per second, and they're both backed by 3 pods each. So in the REST case, each pod is receiving roughly 20 requests per second, but because of the load balancing issue that I mentioned, all 60 requests per second are being sent to a single gRPC backend pod. And that pod has 2 TCP connections total. So like, yeah, so this is a problem, but actually we can fix this by just adding Linkerd to the gateway deployment. So if we redeploy the gateway to use a Linkerd proxy, then the Linkerd proxy should redistribute the traffic evenly to all of the gRPC backends. So I can go ahead and do that by running kubectl get deploy/gateway. So this is getting the gateway deployment from the Kubernetes API and then adding a proxy with Linkerd inject and running kubectl apply. I think that's the right command. There we go. And so if we run kubectl get pods, you can see that the gateway, the previous version of the gateway pod is terminating and the new one is coming back up, and this one has 2 containers, and one of the containers is the Linkerd proxy. And so pretty soon we should start to see, I'm just going to give it a smaller time window. Yeah, there we go. So now we can see that the traffic is actually balanced across all 3 of the gRPC backends. And we're now getting stats for the gateway pod as well. So by adding the Linkerd proxy there to do the load balancing, we have the additional benefit of getting stats about the traffic that is actually serving. Cool. Okay, so that kind of fixes the load balancing problem. But as far as stats go, we can do a lot more. So we can actually we can get a lot more stats per pod. So let me shrink this down for a second and show you a couple more columns. So we have all the TCP metrics. You can actually see bytes sent and bytes received if you want to see that. And what I like about this view for deployments is that you can see that the gRPC backend and the REST backend are sending variable amounts of bytes. And so like actually gRPC is a more compact serialization format. And so the payloads that are being sent back and forth are a lot smaller than the REST payloads. And you can see that in the TCP stats just in terms of the raw number of bytes sent and received on both of the connections. The other thing that Linkerd will do for you, let me bump this back up, is it has a feature called tap. So we can actually look at not just aggregated sets, but we can look at like the raw requests that the proxies are serving. So let me go ahead and tap deploy / gRPC backend. Oh, what did I do?
Use gRPC.
Oh, yeah, gRPC. And you start to get a bunch of data needed. So this is not the stat level view, but this is actually like every single request and response that's transiting the router for any of the pods in the gRPC backend. So this is super powerful for debugging. And it also includes some gRPC specific information like the gRPC status. So with gRPC, I didn't really talk about this at all, but the gRPC, unlike REST, gRPC doesn't rely on HTTP response codes to communicate failure. Those are sent in a different way, and so that has to be interpreted by Linkerd as part of the protocol. Anyway, and there's a lot more command line functionality, but I wanted to show off just real quick the dashboard, because Linkerd also has this great dashboard that will tell us a lot more information. A lot of the information that's on the CLI is also available on the dashboard. Oh, interesting. So the gateway, yeah, so this sort of tells us how all of our deploys are performing. I'll come back to why the success rate is bad in a moment. But let's go ahead and look at the Grafana dashboard. So we will automatically build Grafana dashboards for every deployment and also for every pod. And so you can actually see the number of requests. One other thing to mention here was that previously the gRPC backend pre-Linkerd was not using TLS, but Linkerd will automatically TLS all of your traffic, and you can see that in the graph from when we added Linkerd on the gateway.
Where do you get the certificate?
So we have our own CA that's part of the Linkerd install. Anyway, so that's about it. I was going to show off Silver's profiles, but I think I'm probably going to wrap it up. There's like a lot more we can do, but I don't want to keep everyone here too late. I'm happy to talk more about Linkerd too after we break, but yeah, basically it's Linkerd. Oh yeah, let me just pop back here real quick, finish it out. Yeah, but anyway, so like by adding Linkerd 2, we made all of our gRPC services more awesome, and we have a lot more visibility into what they're doing and control over some of the client settings, and that's about it. I really appreciate everyone coming to the Linkerd meetup. Like, this is our second ever Linkerd meetup, so we're just getting started. Tell your friends. There's going to be one at the end of June, and yeah. Anyway, I think it's really cool technology. So yeah, thanks. Cool. And then these are other upcoming events, more talks and meetups and stuff like that. So. Cool. All right. Thank you all for coming.
Thank you.